Good morning, my dear students. I am requesting all of you to follow my third class on the topic the solid state. So today I will start my class with the topic packing efficiency or packing fraction. See here, in the formation of crystalline solid, whatever the ways the constituent particles are attached, that is packed, no matter, there will be always a vacant space. There will be not only, there will be a vacant space, empty space. See, when I am going to pack some spherical particles, see here, what I am doing, I am arranging some particles, spherical particles, following a definite rule. What is happening? When I am arranging, see here, there is in this space, in this space, in this space, in all this space, there is no particle. Those spaces are not occupied by particles. Okay, so similar to this in crystalline solid, when the constituent particles are packed, attached, there is always vacant space or empty space. So today I am going to calculate what amount of free space is there, or termed packing efficiency in different solid lattice, in crystalline lattice. So for this, first of all, I have to define what is packing efficiency or packing fraction. Okay, packing efficiency is defined as the percentage of total space filled by the particles. But it is defined as the percentage of total space filled by the particles. Particle বিলাকে total space of কিমান occupy কৰিছে তাৰ যিটো percentage হিচাপ তাকে আমি packing fraction বা packing efficiency বুলি কৈছো. The packing fraction is what? Volume occupied by all the particles of a unit cell. All the particles of a unit cell divided by total volume of the unit cell. Okay, it is fraction. Now it is multiplied by 100 to give the percentage. It is called packing efficiency. Say we can modify this. What happens if you consider a crystalline solid? Then volume will be what? Volume of crystalline, cubic crystalline solid, unit cell. What is unit cell? Cubic. Volume of cubic unit cell is what? If S length is A, then volume will be A cube. Okay. See, we already in my second class calculated the total number of particles in different types of unit cells. You know, in the simple unit cell, there is only one particle. Okay. In FCC, phase center cubic unit cell, 4 particles are there. Okay. Again, BCC unit cell contains only 2 particles. So, since we know the number of particles present in unit cell, different types of cubic unit cell, so I am going to calculate the packing fraction in different types of cubic crystalline solid. See, since I am considering cubic unit cell, so volume will be what? A cube. Let the number of particles per unit cell is equal to Z. Okay, let the number of particles present per unit cell is what? Z. Then, in discussion of packing of crystalline solid, arrangement of constituent particles, the particles are considered as sphere. Okay, so we know that what is happening? Volume of one particle spherical. Okay, volume of one spherical particle is what? 4/3 pi r cube. 4/3 pi r cube. Since the initial contains z number of particles, spherical particles, so total volume occupied by the particles will be what? Since this number of particles, volume of one particle is what? 4/3 pi r cube. Okay, 4/3 pi r cube. Okay, say total volume occupied. I am calculating the total volume occupied by all the particles. Again, you know the total volume of the unit cell, cubic unit cell. So I am getting packing fraction, packing efficiency. See here, what is happen? Packing fraction is equal to what? Since number of particles is z, total volume occupied by the particle is what? 4/3 pi r cube. Z into 4/3 pi r cube. So divided by total volume of the unit cell, and what is this? I am multiplying by 100 to get the percentage. Okay, note the volume occupied by all the particles is always smaller than total volume of the unit cell. See, তার কি হৈছে যেতিয়া আমি পাৰ্টিকল বিলাক সজাইছো সজাওতে সি যিমানখিনি ভলিউম দেখাত অকুপাই কৰিছে সি যেটো শেপ লৈছে যেটো সাইজ লৈছে গোটেই স্পেসখিনি সেই গোটেই ঠাইখিনিত ভলিউমখিনি পাৰ্টিকল নাই মাজে মাজে খালি এম্পটি স্পেস আছে ফ্ৰী স্পেস আছে সো আই এম ক্যালকুলেটিং packing fraction. So first of this I will calculate the packing fraction in simple cubic unit cell. See, already we know packing fraction is what? Packing fraction is what? Z into 4/3 pi r cube divided by a cube into 100%. Okay, we know that number of particles per unit cell is equal to per unit cell is simple of how many particles are there in one unit cell? Only one particle. So number of particles per unit cell, okay, is 1. Okay, next pi r cube a. Again we can express a in terms of r, which will automatically cancel out. See, in the previous class we get for simple cubic lattice, for simple cubic unit cell, we found the relation a is equal to twice r. Okay, so packing fraction is equal to 1 into 4/3 pi r cube divided by twice r whole cube into 100. Okay, so after simplification you will get a result, and that result should be remembered by you. Okay, see, the result is almost 52.4%. If I ask you what is happened, since packing fraction or packing efficiency is 52.4%, that is what if the space is occupied by the constituent particles? 52.4. Okay, out of 100. So there will be what? There will be what? Some empty space. Empty space. Taking efficiency this. So empty space will be what? Vacant space. Empty space is also called void. In later class, we will term this as void. There will be different types of voids, which may be triangular, tetrahedral, octahedral void. In the topic close packing of crystalline solid, we will get different types of voids. So this empty space is called also as void. Okay. So empty space will be what? Already particles are present in 52.4%. So empty space will be what? 100 minus 52.4. Okay. What will be the result? 100 minus 52.4. So result will be 47.6%. Okay. So next, I will calculate packing fraction in what? BCC or FCC. Already for BCC we know this. For FCC also it is known. Number of particles per nature is also known. So now we can calculate packing efficiency or packing fraction in all the three types of cubic unit cell. Okay. So in number 2, what is happening? I am going to calculate packing efficiency in FCC unit cell. Okay, FCC lattice. Okay, so here this term FCC, face centered cubic, is also termed as CCP when it is unit cell. FCC, BCC simple, but there are, when we are referring as lattice, then this FCC lattice indicates you CCP. Okay, again after calculation of packing efficiency, we will get the packing efficiency of CCP is equal to the hexagonal close packing. Okay, so see, I will just calculate packing efficiency in case of FCC lattice only, because your syllabus providing only this, not HCP. Okay, so FCC or CCP or HCP, I am going to calculate. What is happening? Packing efficiency is what? This. Okay, so to get the numerical value, we have to know the number of particles per unit cell. FCC, you have to remember this 4. How it was 4? The particles are at the corners, 8 into 1 by 8, plus the particles are present at the center of faces. Okay, so center of face 6 face, 6 into half. So total number of particles is what? 4. Okay. Again, you have to remember this relation. What is the relation? The relation between edge length A and radius of spherical particle. Okay. That relation was what? A is equal to 4 by root 3 R. Sorry. In case of simple, it was A is equal to twice R. Okay. In case of FCC, what was the relation? A is equal to 2 root 2 R. And in case of BCC, that relation was A is equal to what? 4 by root 3 R. So I am requiring the relation. What is this? The relation between edge length A and radius of spherical particle. Okay, what is that? A is equal to 2 root 2 R. So putting the values of Z and A. Okay, we are getting numerical value. So what is this? 2 root 2 r whole cube. So after simplification, you will get a result. Okay, it is 74%. You have to remember this also. See, since 74% space is occupied, since packing efficiency, packing fraction is 74%, so the amount of space, empty space, vacant space, okay, will be what? It will be, vacant space will be what? Empty space will be what? 100 minus 74%. Okay. Okay. So result is what? 26%. This is percentage of empty space. Void. Okay. So next I have to calculate the packing efficiency in case of what? BCC. Similar to this, we can calculate the packing efficiency in case of BCC in itself. Packing fraction, packing efficiency in BCC. See. We know packing fraction is this. Next, number of particles per unit cell of BCC was what? 2. Okay. You know the relation. What is this? A is equal to what? The relation between A and R in case of BCC is what? Tell me. Yes, you know 4 by root 3 R. 4 by root 3 R. So putting the values of Z and A. Is that 4 by root 3 R whole cube. You will get the numerical value, packing efficiency of BCC. It was what? 68%. Okay. Similar to this, I can mention the void, percentage of void, percentage of empty space. Okay, vacant space. It will be what? 100 minus 68%. Okay. This will give what? 38%, 32%. Okay. So vacant space, percentage of vacant space is what? 32%. Okay. See, we are getting the numerical value, but if you look into the number of particles present per unit cell, from that point also you can tell which is best, where packing efficiency is better, best. Okay. In case of FCC, number of particles is 4, but in case of BCC it is 2, and in simple 1. Since number of particles per unit cell is fewer in case of simple and highest in case of FCC, so packing efficiency is best in case of FCC and is lowest in case of simple cubic in itself. Okay. So in this way we can calculate the space, we can identify the vacant space, void, what amount of void is there, how many part is occupied by the particles of the crystalline solid. Now we are able to calculate. Okay. After this, I will discuss you just the next topic. Okay. I will discuss is what? Density. All of you know density. What is density? You know density is equal to mass divided by volume. See, today I am going to calculate the density of crystalline solid. For this, you can consider only the unit cell, because unit cell contains all the symmetric characteristics of the crystalline solid. Okay, so to calculate the density of a crystalline solid, we have to consider the unit cell only. Okay, so mass, let mass of one constituent particle. One constituent particle is what? Let's small letter m, small m. Okay, mass of one constituent particle is m. Okay, total mass. What is the total mass? Total mass of the unit cell. Total mass of the unit cell will be what? Total mass of the unit cell will be what? Okay, let number of particles is z. You know number of particles z. So mass of one particle is m. So total mass of the unit cell will be what? Zm. Where you know already. Where z is the number of particles. You know. Per unit cell. Okay. I am getting mass of the unit cell. Next, I have to calculate the volume. If it is cubic unit cell, if it is cubic unit cell, then what will happen? Volume. Volume of the unit cell will be what? Volume of the unit cell will be what? A cube. What is this? Where A is the K. You know, A is equal to A's length. A is A's length. Okay, so I am getting the total mass and total volume of the unit cell. So I can calculate the density of a crystalline solid. So density D is equal to what? Mass of unit cell divided by volume of unit cell. What is this? Mass of unit cell already calculated. What is this? Zm divided by total volume is what? A cube. Where Z is the total number of particles per unit cell, m is mass of one particle, and A is the A's length. Okay. See, to make this equation more effective, you have to use molar mass, which is known to all of almost all substance. If it is not known, we can calculate molar mass. So instead of mass of one particle, I will try to put here molar mass m. What does it mean? Molar mass is what? What is molar mass? Molar mass is the mass of a substance of 6.022 into 10 to the power 23 particles. Mass of human particles. That is also termed as Avogadro's number. So mass of what? Na particles. You know, mass of Na particles. Molar mass indicates what? Total mass of 6.022 into 10 to the power 23 particles, which is represented by Na. Okay. See, mass of Na particles. Mass of one particle into Na. Okay. So it was already, what is happening? Mass of one particle was supposed as small m. Okay. So total mass, molar mass will be what? mNa. Therefore, you can put m is equal to what? Capital M molar mass divided by Na, Avogadro's number. You are getting this. Okay. So D will be what? You know, D is equal to Zm by A cube. So Z already known for the three types of cubic unit cell. So I am giving M by Na. Okay. So A cube. Thus, we can calculate the density of a crystalline solid Zm divided by Na A cube. Density of crystalline solid, number of particles per unit cell, molar mass of the solid. Na is the Avogadro's number, you know, 6.022 into 10 to the power 23, which is a very large number. Next is the edge length of the cubic unit cell. Okay, so using this relation, you can calculate the density of crystalline solid. Okay, so what is happening in my this class? Just I am mentioning two points. Number one is what? Packing efficiency or packing fraction. What is the definition? Packing efficiency is defined as the percentage of total space filled by the particles. Why it is required? Because all the space of a crystalline solid is not occupied by constituent particles. Okay, there is always empty space. So we have to know which packing is better, which close packing is best packed, or which one is lesser packed. So knowing the packing efficiency, calculating the packing efficiency, we can tell about that. Okay. So after that, I have calculated the packing efficiency of three different types of cubic unit cell. Okay. In simple cubic unit cell, packing efficiency was what? 52.4%. Okay. Next, in case of FCC, what was the value? 74%. And in case of BCC, what was the packing efficiency? 68%. So best efficient packing is what? FCC. You can tell also this point. You can conclude this also from the number of particles present per unit cell. Okay. So after that, I have showing how to calculate the density of crystalline solid. To calculate the density, to measure the density of a crystalline solid, no need to consider the whole crystalline solid, just you consider the unit cell. Okay, so considering the unit cell, we are already calculated the density. We are getting this formula. Then density D is equal to what? Zm divided by Na cube, where Z is the number of particles per unit cell, N is the molar mass, N is the Avogadro's number, and A is the edge length. So using this numerical, you have to solve a huge number of, using this relation, you have to solve a huge number of numericals. One numerical appears in the exam also. Okay, it is very simple, just a mathematical problem, nothing but. Just you have to remember this formula. Okay, if you forget, then you can derive also immediately, no problem. Okay, so I am going to mention here some numerical problems regarding density. Okay, say I'll give you question set. Okay, covering all these topics. Okay, I will upload that, no problem. Just for simplification, just an example. I am taking one example of a numerical from density section. It was what in your textbook. It was in 1.5. Okay, I have remembered 1.5. What is this? Silver forms CCP. CCP means FCC. FCC means what? HCP. Silver forms CCP lattice. Okay, with edge length. With edge length of unit cell is 408.6 picometer. Okay, calculate the density. Calculate the density of silver. Okay, you are given atomic mass of Ag. Atomic mass of Ag is 107. 0.9 U. U means mu. Okay. So see, we are going to calculate the density. You are asked to calculate the density of the silver solid. Okay. So to calculate density, we have to know what is the formula of density of crystalline solid. D is equal to Zm divided by Na kq. Okay. See, what is this? Z will be given by the lattice name CCP lattice. That is what? FCC. Okay, that is what? Similar to what? HCP. Okay. So CCP is, in case of CCP, Z is equal to what? Total number of particles per unit cell of FCC unit cell is what? 4. You know, molar mass. Molar mass M is equal to what? It is relative molar mass, atomic mass. So molar mass is what? 107.9 U. So in gram, that is gram molecular mass, that is molar mass will be what? 107.9 gram. Okay. Next, you know Na. You know Na, 6.022 into 10 to the power 23. What is this? Number of particles per mole. Mole inverse. So next is what? Gram per mole, is na? Am I correct? So molar mass is what? 107.9 gram mole inverse. Okay. Next, A is what? A is given as what? A is 408.6 picometer. 408.6 picometer. Okay. Milli, micro, nano, pico. 4 into 3. What is this? 408.6 into 10 to the power minus 12. 4 into 12 meter. You are using gram, so you can convert this into centimeter. So 408.6 into 10 to the power minus 10 centimeter. Putting this value, we will get the value of density. There will be no problem. Just simple. Okay. In some cases, suppose, okay, it's okay, no problem. Just a simple mathematics, nothing but. Okay. So similar to this, there are a huge number of problems in your textbook. Okay, I will mention the required numericals. Okay, next, there is one problem. In text number, I think in text 1.18. In text question number 1.18. Okay, I am just going to mention the question. An element with molar mass. An element with molar mass 2.7 into 10 to the power minus 2 kg mole inverse forms a cubic unit cell with edge length 405 picometer. Okay, if its density, you are given density, if its density is 2.7 into 10 to the power 3 kg per meter cube. Okay, what is the nearest, what is the Nassar of the cubic unit cell? What is the Nassar of the cubic unit cell? Oh, sorry, Nassar of the, yes, unit cell, cubic unit cell. Nassar of the unit cell. Oh, Nassar of the cubic unit cell. See, Question is interesting because just you are asked nature of the unit cell, given density, so you can also able to identify the nature, means whether it is simple or FCC or BCC, just knowing the value of Z. So from density we can calculate the value of Z, and if it is close to 1, after rounding up, if we get 1, then it will be simple. If it is the number of particles Z is 2, then you will able to mention the cubic unit cell as what? BCC. If number of particle per unit cell, that is Z, is getting, you are getting here 4, then it will be FCC. So in this numerical, I think the result will be what? Z was approximately equal to 4. Okay, 4 point something. So you are getting the value Z is equal to 4. So what is the nature of the solid whose density is given? Okay, it is what? Face center cubic lattice. Okay, so number of particles is 4, so it is FCC. Okay, so after this class I will upload you the notes and the questions. Okay, so majority of you are solving the problems already given. So thank you. Okay, bye.